In this video, we will try to understand PID controller system using particle swarm optimization algorithm, that is PSO algorithm. Here, PSO algorithm is used to understand the optimization of PID controller system and how we can tune PID controller parameters using PSO algorithm. Next, you can see topics covered in this video. First, we will start with basic, like what is PID controller, why we are using this, its advantages, disadvantages, because if we know the basic, what it is, how it is working, its advantage, disadvantage, and what is parameter tuning, why we are doing the parameter tuning for the PID controller. If we know the basic, then we can easily select any optimization algorithm or other method for PID controller, parameter tuning, or for other purpose. So first, it is important to know the basic. So first we will start with what is PID controller, why we are using PID controller, its advantages, disadvantages, and applications, what is parameter tuning for the PID controller, different types of PID controllers, how to tune PID controller. Then we have PSO based PID controller tuning, different methods and optimization algorithm that we can use for the PID controller parameters tuning. And the last, we have different steps that we can use for the PSO based PID controller tuning. So first question is, what is PID controller? Here you can see PID controller. It stands for P, that is proportional, I, that is integral, D, that is derivative. PID controllers are widely used to regulate processes and maintain desired set point. PID controller is designed to force feedback to match a set point. For example, thermostat controller used to force a heating and cooling system to turn on or off at fixed temperature. So in simple words, we can say PID controller is a feedback control system that is widely used in engineering applications to regulate and stabilize dynamic processes. So why we are using PID controller? To control and regulate processes. Here we can regulate temperature, pressure, flow, speed, and other. Next, you can see it is widely used in industries due to its simplicity and adaptability to multiple scenarios. So it is the advantage. It is simple and adaptable. That's why it is widely used in industries. So next we have PID controller requirement. PID controller required accurate mathematical modeling of the system and proper parameter tuning, because when system performance is unclear, there is parameter difference, or we can say fluctuation change. For better results, we need accurate mathematical models and parameter tuning. Next we have PID controller disadvantages. It is time consuming process and can be difficult to implement. Next you can see we have simple feedback system. So here we have simple control loop, have two major components, process and controller. And you can see both components are connected in closed feedback loop. Here you can see this is the set point, that is the desired value of process variable. And here you can see this is the process output, that is the variable measure, and this variable is measured by sensor. And here you can see E, that is a control error. This is the difference between set point and process variable. And next you can see here small u, that is a control variable. And here you can see we have a feedback loop. This feedback loop in system keep process variable close to desired variable in spite of any disturbance. So this is the simple feedback system. having two components, process and controller, and we have a feedback loop. Here you can see we have a controller. This controller has many parameters that need to be adjusted, and if you choose the parameters accurately, the control loop will perform well, else we have poor performance. Or we can say system may become unstable, so we need accurate parameters for the controller. Parameter tuning is done to find out controller accurate parameters. Either we can choose some parameter to observe feedback system behavior and to modify parameters until desired behavior obtained. Else, second option we can develop a mathematical model that describe behavior of process. Then the parameter of controller are determined by using some other methods for the controller design that we will discuss further in upcoming slides. We have the three terms, that is the three main parameters used in PID controller. So we need to adjust these three parameters for the PID controller for better performance. Parameter tuning in PID controller involves adjusting three main parameters. Here you can see first one, proportional gain, second, integral gain, third one, derivative gain. This is done to optimize the controller performance in specific system. In this diagram, you can see we have three main components: PID, proportional, integral and derivative. PID is simply an equation that controller used to evaluate the controlled variable. It is simply just an equation that the controller using to evaluate the controlled variable. Here you can see the set point, then we have error value, control variable, then we have measured process variable. Here controller first compute the error value, that is the difference between measured process variable and set point. Then it try to minimize error by increasing or decreasing the control output or input in process. So the process variable move closer to the set point. And you can see we have three terms P, I and D. The contribution of three terms will yield to control output or the control variables. So first we have proportional gain. In the diagram you can see here P, that is the proportional gain. It determines the controller's response based on current error. This term is directly proportional to the current error, which is the difference between desired set point and the actual process of variable. So we can adjust this proportional response by multiplying an error by the constant, that is proportional gain Kp. So this is called proportional gain constant, and this part is quick responder. Higher proportional gain value lead to stronger response. For example, if the room temperature is too cold, controller quickly turn up the heat. But if it is too high, system can become unstable. Second parameter we have integral gain. This parameter integrate the error over time. And here you can see second term I. This is proportional to the sum of previous error over time. It also helps to reduce steady state error that may exist in the system. And this term is useful for system with imbalance and long-term in fluctuation, because this is learner. If there is any ongoing problem, it slowly adjusts things over time. Third parameter we have derivative gain, that anticipate future error by considering the rate of change of error. So third system is here like a quick predictor. You can see the value for the derivative here. It is proportional to the rate of change of error. It predicts the future behavior based on current rate of change. It reduces system overperforming. For example, we have a problem. For example, temperature is going too high. There is a possibility of any disaster like fire. Then the predictor can easily predict the future behavior based on the current rate of change, and it can reduce the system overperforming. So in PID controller we have three parameters: proportional gain, that is a quick responder, it check the current errors. Next we have integral gain, that is the quick learner, that is the sum of previous error. Then the last one we have predictor, that is the quick predictor, and here it can work on future error, that is the rate of change of errors. Next you can see the mathematical form for the overall control function. UT you can see here, that is control variable, it is equal to proportional term plus integral term plus derivative term. You can see all the value here for the P, K, P, E, T. Then next you can see for the integral term, the third one for the derivative term. The error value, that is the difference between set point and the process variable, and Kp, that is the proportional gain constant, and this is the integral gain. And here you can see we have the integration variable, small t, that is the time, Kd, that is the derivative gain. Next you can see the transfer function in Laplace domain of PID controller. So here you can see this is the transfer function. Next you can see the overall control function. This is the standard mathematical form for the control variable. As you can already see in the diagram, we have the values for P, I and D. Here you can see the output value for the proportional term is calculated using this. Output value for the integral term is calculated using this. Then for the derivative term, it is calculated using this equation. Then here you can see control variable, that is proportional term plus integral term plus derivative term. As you can see here in this equation, proportional, integral and the derivative term. Now you can see we have there are different types of PID controller. For example, we have on-off controller, proportional controller and standard PID controller. Now we have how to tune PID controller. Either we can do manual tuning or automate tuning. Now we will discuss the working principle of PID controller. PID controller operate on the principle that each three term, proportional, integral and derivative, need to be tuned individually, and a correction factor is computed and applied to the input based on the difference between these values. Manually we can do parameter tuning by setting reset time to the maximum value and rate to 0, and then increase the gain until the loop fluctuate to a constant amplitude. Here PID controller continuously calculate the error on the difference between a desired set point and the measured process variable, and apply correction based on three terms: proportional, integral and the derivative. Next we have PID controller implementation. We have how we can implement PID controller. First choose the structure. So first we will choose the structure of PID controller. Next we will choose the numerical value, or we can say PID coefficients, to tune PID controller. That is the tuning. We need structure, then we need proper parameter tuning. In tuning we choose the numerical value for the PID parameters. PID constant are tuned in terms of their proportional gain, integral gain and the derivative gain. So first you can see here we have proportional gain. If the value for Kp is larger, then we have faster response. But here larger proportional gain sometimes result in process instability. Next we have integral gain value. If this value is larger, then we have steady state error, and if the derivative gain value is larger, then it decreases the overshoot, what slow down the transit response. So we need to do proper tuning for all three terms for the better performance. Now next you can see different optimization algorithms and other methods we can use for the PID controller parameter tuning. Now next question is how we will decide which algorithm or method we can choose for the parameter tuning. Here the choice of tuning method or any algorithm depends on specific characteristics of system, the available information about process, and desired performance criteria. We can either combine multiple methods or use iterative approaches to fine-tune PID controller parameter for the optimal performance. First you can see we have optimization algorithm that we can use for the parameter tuning. Various optimization algorithms are used such as genetic algorithm, particle swarm optimization algorithm, and we have simulated annealing. So we can use any algorithm to find the optimal PID parameter by minimizing cost function that represent the system performance criteria. Else we can use different methods that are given here. First we have Ziegler-Nichols method. This is a heuristic method involve increase the proportional gain until the system start oscillate. In second method it is just similar to first method. Here it involve determining the ultimate gain and ultimate period from which from system frequency response to calculate PID parameters. Root lotus method, and you can see gradient descent method. We have a number of methods that we can apply. Now last we will see the PSO based PID controller, how we can apply PSO algorithm for the PID controller parameter tuning. So first you can see about particle swarm optimization algorithm. We already discussed in different videos what is this algorithm, how it is working, its mathematical models, everything we discussed in detail. Even we did using numerical examples, MATLAB code or in the Python code, and also applied to economic load dispatch problem. So what is this algorithm, how it works, its basic detail you can check in previous videos. Now you can see the basic steps of PSO algorithm. First initialize all the important parameters, PSO parameter. So here we have PSO parameters and the current problem parameters. Next we will randomly initialize the particle's position in the search space. After that declare your objective function based on the current problem. Then evaluate fitness value, calculate best and the global best, personal best and the global best, update velocity position for each particle, calculate the fitness value using objective function for the new position, check the boundary whether the new solutions are within the boundary or not, and then again update personal and global best. Repeat the loop until stopping condition is met, and in the end display the best solution. So here you can see first step. So first step you can see initialize important parameters. For example, you can see we have different parameters: population size, that is the total number of particles in the current population, current iteration, maximum iteration, dimension, or you can say the design variables, weight inertia, coefficients. We have the PSO parameters. Then we will randomly initialize the particle initial position in the search space. After that, here we will define objective function. So declare your objective function. Here you can see this is the fitness function, this is the scaling factor, peak, overshoot, setting time, rise time. So we use PID controller to regulate processes like temperature, pressure, speed. So accordingly here we will declare your objective function, then apply this objective function on the current population, find out the fitness value. Then in the fitness value we will select the personal and the global best. Then here update velocity using this equation, then update the position in the previous velocity in the previous position at the calculated velocity, and it will give you new position. After that, we will calculate the fitness value for the new solution and then check the boundary whether the new solutions are within the search space boundary or not. Then again update global and the personal best. Check the stopping condition. If it is not met, then repeat the loop, else display the best solution. So instead of PSO algorithm, you can apply other method or any other optimization algorithm and properly define your objective function according to your problem. So that's all about this video. If you have any questions, you can comment below, and thanks for watching this video.